Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali Muqaibel, and today's lecture is about antennas for communication engineers. This is part 2 with some more focus on satellite communication. In the first part we discussed a few things about the basics of antennas for communication engineers, and we'll shed some light now on radiation efficiency, antenna directivity and antenna radiation intensity, gain, aperture area, effective area, aperture efficiency, and then we'll review isotropic radiators. We'll look at types of radiation patterns, and we'll look at antennas patterns, nulls and loops. We'll look at antenna beam width, and we'll conclude with the type of antennas, and we'll get some examples related to satellite communication, to how to design the antenna. So basic definitions. Well, let's start with the radiation efficiency. P naught is the power that we feed to the antenna. Now, not all the power that we feed to the antenna will be translated into radiated power. So the antenna is fed by P naught, which is the power at the input of the antenna, shown in green. And the output power would be PR, the radiated power. The ratio between the radiated power relative to the input power is known as the radiation efficiency. So the efficiency eta is PR divided by P naught. This is called the efficiency. And if we have lossless antenna, then whatever we put inside will be radiated. And in that case, the maximum efficiency would be 1. Of course, practical antenna will have efficiency less. So this is the first definition of the radiation efficiency. PR over Pn. The second important definition is the antenna directivity. Maybe we have shed some light on this, but we can review that by saying the directivity of antenna is defined as the ratio of the radiation intensity in a given direction from the antenna relative to the radiation intensity averaged over all directions. So we have a sphere. Sorry, this diagram is shown in 2D, but in general we have 3D. So we have a sphere if you have an isotropic radiator. Antenna directivity means that we are going to have more concentration or intensity of radiation in one direction at the price of less radiation in another direction. So the radiation intensity can be represented as function of phi and theta, if you like, elevation and azimuth, 2 angles. And we compare that relative to the average radiated over all angles. And if you consider a sphere, then we talk about solid angles. In a circle we have 2 pi, in a sphere we have 4 pi. So we can compare that relative to an isotropic radiator. The directivity would be more than 1 in directive antennas. It will be much more than 1. If it's much more than 1, we call it directive antenna. And it's equal to 1 if there is no directivity, like in isotropic radiators. Of course, if we get higher than 1 in one direction, then you expect that the intensity in other direction would be less. So antenna directivity is a measure of how directive the antenna is, how we can concentrate the power in one direction. This is the second definition. We can include both directivity and the gain of the antenna and the efficiency of the antenna, and we call that the gain. So the gain is the ability to concentrate the power in a given direction. So directivity shown in green. If it is scaled by the radiation efficiency, we can get what we call the gain. Alright, so if the gain is equal to 1, if the efficiency equal to 1, then the directivity and the gain becomes equal. Here we are showing the diagram for the dipole, okay, the omnidirectional antenna, where it shows some concentration of the energy instead of sending up and down to the sides. The isotropic radiator gain, we can think of the isotropic radiator as having, we can think of a theoretical antenna which does not exist, that radiates equally on all directions, and if we assume the efficiency equal to 100, then the output will be the isotropic radiator. We can have more realistic example if we think about the dipole or the half wave dipole, and it will show the radiation pattern like a donut, so it concentrates the energy that goes up and down into the sides. So it's omnidirectional in all directions, at the expense of taking the energy. There is some sort of directivity here. These diagrams is just to show you the exact details of the radiation pattern. Now, we can use these antennas as a reference. Remember the dB scale, it's just a ratio. But if we are comparing the gain relative to the isotropic radiator, we call that dBi. So how much we gain relative to the isotropic radiator. And if we are comparing with the dipole, then we call it dBd. So get used to that. We have dB, which is unitless ratio. We have dBi relative to the isotropic, and we have dBd relative to the dipole. Remember, they are not the same because there is some directivity here. So 0 dBd is equivalent to 2.15 dBi. You can read more about that. I'm just here to share with you the basic terminology. Power density and antenna effective area. We can also represent the power density, how much density relative to a given area. So we can think of the power density as the distribution, of the antenna for the given angle, and we can multiply that by a factor, which is P naught, the input power, divided by 4 by R squared. This is the ratio of power if we have lossless isotropic radiator. This is the intensity because the power will be distributed over a sphere, and that's the area of a sphere. So it's P naught divided by 4 by R squared. But if your antenna has certain directivity, then we have to scale that accordingly. Of course, we're not including here eta because we are assuming lossless antenna. Now, we can think of the area, and we can represent the antenna in terms of area. So we can think of the antenna effective area, which is a measure of the effective absorption of the area of the antenna relative to incident plane wave. So we can measure the density of how many watts per meter square, and then we can know the area of our antenna, and then we can find how many watts. But not all the area will be effectively used. So we define the effective area of the antenna, and it's related, of course, to the gain of the antenna. The exact relation is given here. The effective area of the antenna, if you give me a certain power density, I have to see how much effective area I have. It's not the physical area. So it's lambda, it's related to the wavelength. It's also a function of the gain of the antenna, because antenna could get more power or less depending on its directivity. Now, the effective area relative to the physical area, we can call that the aperture efficiency. We have the antenna efficiency, which is PR over P naught, and now we have the aperture efficiency, that's the area efficiency. So it's the effective area relative to the total area, the physical area. Now, recall that we can focus now on aperture antennas, especially in satellite communications. We think about horn, dishes, and similar antennas that are called aperture antenna. They have a certain opening or aperture, and we relate the efficiency of the antenna relative to its dimension. So the gain of these antennas is it's eta A, the efficiency of the area, multiplied by 4 by A. So you can remove A and put effective area if you like. 4 by divided by lambda squared. Just to share with you that antenna's efficiency usually between 50 and 70%, usually. And for aperture antenna, the efficiency for reflector antennas is between 50 and 68. This is just rough to give you an idea about what numbers we are talking about. For horn antenna, it can exceed a little bit, and it goes from 65 to 80%. Now, if your antenna is circular and the dimension is d, we can represent this equation in terms of, because the area of a circle is, as you know, by r squared. Or if you want to remove r and put d, then it's going to be d over 2. So it's going to be by d squared over r over 2 squared, and then the 4 cancels out, and we get the following equation. So to go from here to here, we just replace the area with its equivalence in terms of a circle, which give us the equation below. The area of a circle is by r squared, or if you like, you can remove r and put d over 2 all squared. So this is why the 4 cancels out. So what we have here is an equation for the gain in terms of the dimension of the antenna. That will make things simple. If you have a circle, then you just take the diameter. And if you have horn or square, then usually we take the maximum physical dimension of the antenna. This is just rough calculation. Recall that the 3 dB beam width of an antenna can be related to D, again roughly. The beam width is the width of the antenna in degrees. So we can say that the 3 dB is equal approximately, this is just rough, 75 times lambda over D. So it depends on the dimension of the antenna, it depends on frequency of operation. Again, I can go to this equation, replace D with its equivalent 75 lambda over phi. Lambda will cancel out, and from this equation I will get the gain. This is exactly the same equation, but I replaced D with its equivalent here. So lambda cancels out. And if we have a lossless antenna, we can represent the gain by the following equation. Okay, so that is cool. We can just give me I can relate the gain requirement to the dimension to d theta. So in satellite applications, we need to define the coverage, so which is related to the angle and the beam width, and of course from that we can design the dimensions. Give me the frequency, or I can find the dimension of the antenna. Okay, this is how we got from here to here. This constant is nothing but assuming 60%, sorry, not lossless, 60% efficiency, which is a typical number, and we got these numbers. So remember that these numbers are not exact numbers, and the design of the antennas usually is not about being exact, because we want to get rough estimate, so we plan accordingly. There will be rain, there will be other stuff. It's not like orbital mechanical numbers where we are worried about the accuracy. Even this number could vary from 28,000 to 35,000, okay, depending on the type of antenna. So now time for the examples. The Earth subtends an angle of 17 degrees when viewed from geostationary orbit. We are at the dimension. We want to find the dimension and gain of the horn antenna that will provide global coverage at 4 GHz. So if you are at the geostationary satellite, then the angle required to cover the entire Earth is going to be 17 degrees. So now we can use our equations. Remember that d over lambda equal to 75 over the beam width. We'll assume that we have 3 dB beam width, which means the power received at the edges is going to be half the power at the maximum. Remember, we're substituting degrees here, so 75 divided by 17 give you 4.4. The ratio between the dimension and lambda should equal to 4.4. But now we have frequency of 4. We can use the speed of light and c equal to lambda f to come up with lambda, which is nothing but 0.075 centimeters. And sorry, it's going to be 7.5 centimeters. Okay, so we divide by 100, we get 7.5 centimeters, and the dimension of the antenna will be 4.4 times that number, which is 0.33. So you can think now of the size of the antenna that we are after. A horn could be used in this application. Reflector antennas are not efficient when the aperture diameter is less than 8 lambda. In our case, we have the diameter is, we can relate that the diameter is 4.4 times lambda. Okay, so this is not very efficient. If you want to find the gain, again, we just the gain of horn antenna is approximately given as 100 or 20 dB at the center of the beam. When using the edge, if you take 3 dB, it means we'll have 17 dB at the edges, of the coverage. Since this is the Earth stations close to the Earth horizon, we have a 3 dB reduction viewed from the satellite. The one in the middle is 20, while the ones at the edge will be 17. Now to the second example, the continental United States 48 contiguous states, subtends an angle of approximately 6 by 3 degrees when viewed from the geostationary orbit. What dimension must a reflector antenna have to eliminate half of this area with a circle beam of 3 degrees in diameter at 11 gigahertz? So now we need to use the equation to find how much is we are given the frequency, okay, so we can find lambda. We are given the coverage, which is 3 degrees, and we would like to find the required design. So if you look at the ratio, d over lambda would be 25, and then if we substitute lambda for that frequency, just like we did in the previous example, the dimension will be 0.68, 68 centimeters. Now the gain of this antenna is approximately 35 dB by looking at the equation. To generate a beam with different beam width in orthogonal planes, we need to have aperture of different dimensions because we have 6 by 3 degrees. So a rectangular aperture of 25 lambda by 12.5. 25 lambda is what we got from here. 12.5 lambda, which is half of that, because we designed for 3, and now we just need half the coverage. So that would be 12.5, and then we have here 6, which is going to give you 25 lambda. So we have done things here for 3 degrees, and it turned out that the relation is 25 lambda. If you repeat this for 6 degrees, it's going to give you a relation of if you repeat that for 6 degrees, it's going to give you 12.5 lambda. And remember that we have a gain of that requirement. So we can use rectangular or elliptical outline reflectors, and that are used to generate unequal beam width. Because we have different dimensions here, we can have kind of rectangular coverage. That's of course approximate. Now of course, when we come to the link budget, we will need to extend these relations to go from the transmitted power to the received power. So the received power will be related to the transmitted power multiplied by the efficiency. We'll spend some more time here when we discuss these equations. So it depends on the gain of the transmitter, gain of the receiver, and also it depends on which frequency you operate and how far the object is, how much is the original power. We'll speak more about the received power as we go into the link budget. Now, back to some of the antenna's parameters. The antenna beam width, we discussed the antenna beam width, which is measured in angles. If you look at the antenna bandwidth, then it is the range of frequencies within which the performance of the antenna with respect to some characteristics, we're saying some characteristics because it depends on what you want to do, conforms to a specific standard or be-specified standard. So some people look at the bandwidth for the gain, return loss, beam width, side lobe level. It depends on what you want to do. So the bandwidth is how much bandwidth that guarantees certain characteristics. So we look at the highest frequency minus the lowest frequency divided by the center frequency. That would give you the kind of fractional bandwidth, or the bandwidth in percentage relative to the center frequency. We have the bandwidth, and we also can have the fractional bandwidth, or the relative bandwidth relative to the center frequency. If you are interested in bandwidth relative to mismatch loss and what have you, there are other terminologies, which is standing wave ratio, and it's beyond our objective here. An antenna course will cover more details about that. Another concept that we might think of is the reciprocity. An antenna will act as a transmitter in a very similar way when it's used as a receiver, except There are some special cases, of course, if the antenna has certain type of magnetic material, or there are some rust and some problems with, or if there is active element diodes because they operate in a different way. But in general, if the antenna has a certain gain as a transmitter in a given direction, it will act similarly as a receiver. Of course, we can exclude some special cases here. I'm just interested in giving you the basic concept. All the major properties of a linear passive antenna are identical whether it is used as a transmitter or in transmission or reception mode. That's good enough about reciprocity or antenna reciprocity. Now, especially in satellites, we can think of, because we are at far distance and we want to cover different regions for tracking, for weather, so we can think of omnidirectional antenna. And we mentioned that we have the dipole kind of antennas, and we have large coverage. They are popular in communication and broadcast applications. The azimuth pattern is circular, but the elevation is not. So that's like the dipole kind of shape. The second type is the pencil beam. And you can see here like we have like a pencil. It's very directive, applied to high directive antenna pattern, consisting of a major lobe, consisting of the interaction between two different lobes. Usually the beam is circular and symmetric about the direction of the peak intensity. So you can see here we have a pencil here. It's a very directive. It's good for tracking or what have you. We can have a fan. It's like a piece of a fan that's rotating. A fan beam is narrow in one direction and wide in another direction. A typical use of this fan would be search and surveillance radar. When you search a big area, but for a given dimension, it's focused. So here we have wide, but here we have narrow beam. So in one dimension it's narrow, in the other dimension it's wide. Narrow, wide. That's called a fan. It's like a piece of a fan. Or in the general form, we have shaped beams, where we try to control the beam direction to cover a certain area so that the power will not be lost in the ocean if the application is intended for the continent. And it's also used for search and surveillance. So we can think of radiation pattern for satellite application as omnidirectional, pencil, fan, and shaped beams. Okay, another way to look at the antennas, looking at the field of region, we can think of the three regions. If you are very close to the antenna, we have the reactive near field region. If you are a bit just far, then we have radiation near field region. This is reactive and this is radiative. Reactive or non-radiative. And then we have radiative. And then after a certain distance, the field is called the far field. In many cases, we operate in the far field. So we have the antenna, we have the reactive, the radiative, and then we have the far field. So what we want to learn is that if you are very close to the antenna, the shape of the beam would be different. And I would like to share with you that if the region is in very close immediate contact with the antenna, we have what we call the reactive near field. It's up to this distance, lambda over 2 pi. Okay? But of course, between these two limits, it's called radiating near field. If it exceeds this limit, it's called far field region. As I mentioned, in many cases, we assume far field region. There are other names that you can use, like for our region. If you exceed that region, then it's the far field. Generally, measurements are taken in the far field. In case of large planar antennas, it's more convenient to make near field measurements, and then we calculate the far field measurements, because sometimes we don't have enough space to be away from the antenna. But I would like to highlight that just you need to know when are we in the far field. So this is a major condition. You need this equation to know if you exceed this condition, it's related to the dimension of the antenna and the wavelength. Then you are in the far field. Now a little bit of practical information. What you see in the picture on the side is King Fahd City for space communications. Some of the large 32-meter dishes there. It's a satellite connected station. I just want to share with you some information about the ground antennas, then we'll talk about the satellite antennas. Different satellite missions have different allotted frequencies by ITU. So of course, depending on the ground station, depending on the differences of frequencies, we have different dispersion, different attenuation, and different noise accumulation. So if the frequency is low, below 1 GHz, there are certain antennas that are used, like helical antennas and Yagi and dipoles. And of course, they will get wider beam width and medium gain. Usually, we can deploy them in an array, which result in increased gain. We have fan-shaped and shaped beams. We have fan and shaped beams, as we have seen in the previous slide. And that's enabling them to use for tracking applications. We also have frequencies above 1 GHz. And of course, they result in different fading and dispersion. For that case, we use horn and parabolic antennas. And this is why we discussed some time about the aperture antennas, because these other frequencies are usually more than 1 GHz. Now, we have all type of reflectors. Okay, if you focus with me on the diagram on the right, I will try to explain them. And then you can read the details here. I just want you to know that sometimes we have the feed. This is the reflector antenna. All these are reflectors. Sometimes we have the feed where the signal goes, and it reflects and goes back. This is axial or front feed. We feed from here directly, from the front, and we are in the axis. We can also have the reflector, and we move the feeder away, so we have off-axis or offset feed. This is offsetted to avoid being in front of. There are some advantages not to distort the radiation pattern. We also have Cassegrain and also Gregorian feed, where you can see that the feed is here. And then we put a reflector. This reflector could be in different ways. So this convex or concave. You can see the tilting here. We just give them different names. And of course, they result in different performance. Like if we do it this way, then of course we can control the far outside lobes here. So basically we have front feed and we have feed at the reflectors, almost here. The advantage of doing it this way is that we have access to electronics. Remember that these reflectors could be huge, like 32 meters or so. So if we put the feeder away in the focus, then it will be difficult to maintain. Over here, we can just have access from the back of the dish, and we can go into electronics. And then we use reflectors. So there are pluses and minuses for all these. You can read the details here, pause the video, and I'll leave them for you. I just mentioned that here there is access to electronics. And if you are offset, then you are not in the way of the radiation pattern. And then, of course, doing it in a convex and concave result in different lobes in the radiation pattern. If we are at the satellite, then we are limited because we have limited physical dimensions and we have limited power. So medium gain antennas are used, and this includes modified antennas for the large area coverage, modified parabolic antennas. In LEO application, the satellite may be two-axis stabilized, so we can have antennas that rotate to adjust, to despun the antenna, because the antenna is moving quickly, or the entire satellite is moving quickly, so we need to control the rotation of the antenna to keep it directed. We can also have helical antennas like the one shown in the diagram here on the figure on the left, and those are used for circular polarization. For application like geostationary Earth orbit, which are used for digital video broadcasting, usually we have very small aperture terminal, and this is like the dish antennas we have at the roof of lots of the houses. This is used for, we can use linearly polarized arrays for broadcasting surfaces to cover large areas. For broadcast surfaces also, the transmitting antenna may consist of an array of 4 antennas or helical antenna. Array means group of antennas arranged in a certain way. It could be linear or square or what have you. We also have another antenna called disc on rod. So it's like a rod and then there is a disc, which can result in good radiation and use for some satellite applications. Power beams from the antenna can be steered to cover a certain specific area on the Earth's surface by switching one of the elements on and off. So we have steering direction of capability of the antenna, not by physical or mechanical mean. We can just control the array by turning on and off or control the phase. Here we're showing one of the characteristics of the satellite. We have satellite footprint. So we can show the footprint, which is the coverage of the satellite on the map. We have global footprint if you have entire the globe. We have hemispheric beam footprint, and then we have zoom beam footprint. Here I'm showing you another example. Of course, once you change the frequency, the coverage will be different. So we have global, hemisphere, zone, or spot, even spot. You can see that we have large coverage, then we have more of a continent, then we have a zone, and then of course we can have spot. Of course, those are at different frequency bands. Here I'm sharing with you the national and regional satellite systems for different countries and different locations on the map, different continents. All right, now here's a practice. I would like you to kindly stop the video now and then take your time. We have one more slide to conclude to answer the following questions. Please share your answers in the comment section. For the shown figure, what is the beam width? What is the maximum? Where is the 3 dB? And give me your answer in degrees. What type of antenna is the one shown here in the figure? Okay, give all the description that you know. Is it off axis? Is it Gregorian? Whatever the kind of the antenna you have, please describe all the descriptions that you know. And then I'd like you to make sure that you differentiate between radiation efficiency, antenna directivity, aperture efficiency. These are the three we discussed. What is the difference between gain and directivity? What is the difference between dBi and dBd? What is the difference between power density and received power? And then for antenna working at 5 GHz, how much is the distance to be in the far field? You need to go back to the slides. So please share your answer at least to number 7 in the comment section so that we can cross compare. All right, this is a motive for the next video. Hopefully you all will be with us. We talked about the antenna, mostly at the transmitter side. We need now to go to the receiver side to talk about the link budget. For that, we need to know what's the free space transmission loss, receiver, what is the loss due to the feeder, antenna misalignment losses, fixed atmospheric and ionospheric losses, absorption losses, depolarization losses. These are among the things that the signal will have to go through before it gets to the destination. So we'll see you at the other video. This is our motive for the link budget analysis. Thank you for being good listeners, and we'll see you then.